All right, here we have a question from parabola section. Today we are going to solve this. Let's see what's given here. We're given that we have a curve C in the diagram C. C is representing the parabola with the equation y is equal to x square. P is a point with the coordinates 0, 1. Here P is P, and Q is the point a, a square on C. Here we have the Q. L is the normal on C. L is a normal to C. L is normal to C, which means there's a tangent and it's perpendicular to the tangent at point Q. With this information, it's asking find the equation of line L. For what values of A does L pass through P, and some other questions. Let's solve the first part. For the first part, the first part, we have to find the equation of line L. Given that it passes through a, a square, we know the equation of line which passes through point x0, y0 with the slope m is y minus y0 equal to m the slope times x minus x0. This is the equation of line L. Equation of any line which passes through point x0, y0 and it has a slope m. Now, in order to determine the equation of line L, we need to find the slope of L. The point we already know it passes through Q. So how can we find the equation, the slope of normal? We know that the slope of normal is normal is perpendicular to tangent. Let's say this is the tangent. The angle between normal and normal and tangent is 90 degree. If we have two perpendicular lines with the slopes m1 and m2, then their product is -1. Slope of tangent, we can find this with the derivative at a point. This will be, since C is y is equal to x square, the derivative will be the power down, power minus 1. This is 2x. And it passes through A, through Q with the coordinates a, a square. Then the slope at point Q is 2a. Using the concept of perpendicularity, we can find slope of normal is -1 by slope of tangent. Slope of tangent is 2a. So our m, the slope of line L, is -1 by 2a. Now we know that it passes through the point Q with the coordinates a, a square. So the final equation of L is, equation of line L is y minus y0. Y0 is a square times equal to the slope, which is -1 by 2a into x minus a, because our point is a, a square, the point Q. So if I simplify this, this will be minus x by 2a plus a square plus 1 by 2. This is my equation of line for the L, where L is the normal. If I look at the part B, part second of the question, part second is saying that for what value of A does L pass through P? L pass through P for what values of A? Now, if P is, if L is passing through p0 comma 1, then it must satisfy its equation. If I put these values in the equation, then I get 1 is equal to 0 plus a square plus half. This gives me a square equal to half, taking this half on the left side. A is equal to plus minus 1 by root of 2a, 1 plus minus root of 2. So for this value of a, L passes through P. L passes through P. Okay. In the third part, it's saying that determine the distance from P to Q, which is denoted by QP, as a function of A, where A is here arbitrary. We have determined this as a function, the square of the distance as a function of point A. Part third is saying that the distance QP square as a function of A. So how do we know? We know that if we have 2 points, let's say coordinates of P are x comma x0 comma y0, x1 comma y1, and coordinates of Q are x2 comma y2, then the distance from Q to P is square root of x1 minus x2 whole square plus y1 minus y2 whole square. So this is the form of the distance formula. Then QP square will be x1 minus x2 whole square plus y1 minus y2 whole square, where here the coordinates of Q are a comma a square and coordinates of P are 0 comma 1. With these values we get QP square to be 0 minus a whole square plus 1 minus a square whole square. This is a square plus 1. Expanding this will be, on simplification, we get a to the power 4 minus a square plus 1. And I'm denoting this as a function of a, since a is arbitrary. So part 3 is done. For part 4 is saying that for what values of a for which Q and P the distance is smaller, is the smallest between Q and P. Now we find that the square of the distance can be written as a function. Part 4, we have to find Q and P distance is smallest for what value of a. We know that the distance QP square is the function of which a, which I have written here. If I minimize the distance of the square, then I am minimizing the distance QP. The same point will minimize the distance of Q and P. So instead of minimizing finding the smallest value of QP, I will be finding the smallest value of square. Now, since this is a positive term and the same thing will work here, because it's a well continuous and differentiable function, simple function, polynomial function. Now, this is a problem of calculus of finding the maxima and minima. We know that in order to find the minima or extrema, local extrema, the derivative we have to take, and we know that the derivative vanishes at local maxima or minima at extrema. So with that, I will find the derivative, first derivative, which is 4a cube minus 2a. At extrema, we know that this is 0. So for extrema, we have this. Now we equate the derivative, which is 4a cube minus 2a equal to 0, then 2a, I'm taking common, this will be 2a square minus 1 equal to 0. From this, I get either a is 0 or a is equal to this, plus minus 1 by square root of a, square root of 2. Now, we don't know whether they are the point of maxima or minima. For that, we check the second derivative. Second derivative for a point A is 12a square minus 2. The value of second derivative at point 0 is minus 2, which is negative. Then this implies that a equal to 0 is local maxima. F double derivative at point square root of 1 by 2 is same minus 2 is here. So this will be 12 into 1 by 2 minus 2, 6 minus 2 is equal to 4, which is positive. So A is equal to R points of minima. So for these values of A, the distance between Q and P is minimized. If we look at the last part of the question, it's saying that we have to find a point R in the xy plane, but not on the curve, but not on the parabola C, such that the distance RQ is smallest for a unique value of A. Excuse me. So let's assume that we have a point R in the xy plane with some coordinates x comma y. If I claim that distance from R to Q is smallest, let's say with the magnitude of epsilon, then does such a point exist? This is my parabola, point Q. Let's take any point R in the xy plane, and that this distance, let's say, is epsilon. If I claim that this distance is the smallest, then I'm giving you this distance smaller than this, which is half, which is less than that. And if I claim that my R dash is the smallest, R dash is the point from which the distance to Q is smallest, then I can give you smaller than that distance R double prime. In this case, no such R can be found. So no such R exists uniquely, or no such R exists because the distance to be minimum from Q, if there is some distance in any neighborhood of Q, then I can find smaller neighborhood of Q such that distance is further smaller. So no such no such R exists. Thank you.